4.1 Cuts and Connectivity. So we're finally starting chapter 4, and we're going to almost reintroduce this idea that we're a little familiar with. So we've talked about connectivity in the previous chapters, but how can we generalize our idea of connectivity, and what results can that bring about? So, to start us off for today, let's go ahead and talk about vertex connectivity. So the first definition I have for here is what is a separating set? A separating set, or sometimes you might hear me say even a vertex cut, of a given graph G is some vertex subset such that whenever I delete that set of vertices, I have more than one component as a result. So we have a vertex cut or a separating set. And then now we can talk about connectedness. A graph is k-connected if the deletion of any vertex subset of size k minus 1 does not disconnect the graph. So in other words, if I'm talking about, for example, a 3-connected graph, that means no matter what two vertices I delete, my graph will still be connected. All right, so we have a k-connected. And now I want to introduce connectivity of a graph. So the connectivity of a graph, here I'm going to use the notation kappa of G, or just kappa. This is the greatest integer, such that my graph is k-connected. Or you can also think of this as the minimum size of a vertex subset, such that G minus S is a single isolated vertex. So it's actually important that we include the second part of the definition, because, for example, if we have a complete graph, no matter how many vertices you delete, the graph will still be connected, because the edges are connected to every other vertex. So we have k-connected and connectivity k. One thing I want to emphasize is that these two are not the same thing. So k-connected and connectivity kappa equals k do not mean the same thing. While connectivity k does imply k-connectedness, the reverse is not necessarily true. Just because we're k-connected, this does not necessarily mean that we have connectivity k. I know it sounds a little bit weird because we're using almost the same words, connected, connectivity, but these are two separate definitions. One way that you can think about this is that k-connected is a structural condition, whereas connectivity is an optimality solution. Another thing I want to note is that if a graph is 3-connected, this means that, again, by definition, if I delete any 2-vertex set, this does not disconnect the graph. 3-connected does not mean that if I delete 3 vertices, then I'm automatically disconnected. This is not necessarily true. It could be true, but strictly speaking, k-connected, all it means is that if I delete a vertex subset of size k minus 1, I am not disconnecting the graph. So some really important notes here. Again, k-connected is a structural condition, whereas connectivity is an optimal problem. So just so that we have an idea of this, let's go ahead and look at this example here. Here I drew some random graph. And one thing I can say pretty quickly just from looking at this graph is that if I delete any single vertex, I'm not going to end up with more components. And you can go vertex by vertex, one by one, to check this. So if I delete just Y, all of my other vertices are still connected. Same thing if I delete X, if I delete Z, W, V. No matter which single vertex I delete, I'm not disconnected. So that tells me that my graph is 2-connected. Furthermore, this tells me that my connectivity is at least 2. So again, I'm 2-connected because any vertex set of size 2 minus 1 or 1 does not disconnect my graph. The connectedness does provide a lower bound for our connectivity. All right, so we know we have a lower bound for our connectivity. How about finding an upper bound? How will I consider this a vertex subset? What if I look at Y and Z? What happens if I delete these vertices? Remember, whenever I delete a vertex, I have to delete all the edges incident to it as well. In other words, if I delete Y and Z, my resulting graph looks something like this here, where x is isolated by itself, and then wv are still connected by an edge. This is clearly no longer connected. I have two components here. So since the deletion of this set does result in more components, that tells me that S equal to YZ is a separator set or a vertex cut. Therefore, this tells me that kappa is at most 2. The connectivity is at most 2. So I have my lower bound is 2, my upper bound is 2. Therefore, my connectivity is exactly 2. So this is how we might consider it. So this is for vertex connectivity. Well, what's stopping me from doing the same thing with edges? So for our next definition, I have almost the same idea. I worded it a little bit differently here. So a disconnecting set of edges is a set, let's call it F, such that whenever I delete those edges, my resulting graph has more than one component. In other words, whenever I delete those edges, I'm now disconnected. A graph is k-edge connected. So instead of k-connected, we're saying k-edge connected if every disconnecting set has at least k edges. Or I can use the same definition as before. K-edge connected will tell me that if I delete any edge set of size k minus 1, I should still be connected. This is an equivalent definition. The edge connectivity of a graph, here we're going to use a very similar notation. Here we say kappa prime of G, or just kappa prime. This is the minimum size of a disconnecting edge set. Or again, if I use the same definition as my regular connectivity, this is the maximum k such that we are still k-edge connected. Next thing I want to introduce is an edge cut. Here I'm going to use this notation. It looks like a bracket with an S and S bar. Remember the S bar, this represents almost like my complement. So this edge cut is an edge set where each edge has one endpoint in S and the other endpoint is in S bar. In other words, the vertices of G minus the vertices of S. So here we have an edge cut. So just so that we can really give a concrete example here, let's use that same graph I had earlier. And notice here that I've already went ahead and put some lines dotted. So if I look at these 3 dotted lines in my graph, if I were to delete these 3 edges, I think we can pretty clearly see that my resulting graph would be disconnected. So that tells me if I look at a set, F1 is equal to WY, YZ, XZ. This is a disconnecting edge set. This also provides an upper bound for kappa prime. Let me move myself over here so I don't block the text. So here I have an upper bound of 3. There's a reason that I gave this particular set. Yeah, this does disconnect my graph after I delete these edges, but it's not the best possible option. I can improve this. For example, if I want to improve this, perhaps I want to go ahead and look at this set ZV and WV. And this is also a disconnecting set. If I deleted these highlighted edges, then I would still have 2 components in my resulting graph. So that does tell me I also have an upper bound of 2, which is better than an upper bound of 3. Alright, so I have an upper bound of 2. If I want to prove a lower bound, if I want to prove that kappa prime is at least 2, this is equivalent to me saying if I delete any single edge, it does not disconnect my graph. Well, we can verify that very quickly. If I look at any single edge in this graph and delete it, it's not going to create a disconnected graph. That is, as the deletion of any single edge that cannot disconnect my graph, I must be 2-edge connected. Or in other words, kappa prime of G has to be at least 2. Well, since I have my lower and upper bound are the same, then my edge connectivity, kappa prime, is equal to 2. And before I move on here, I just want to again emphasize, just like the vertex K connected versus connectivity K, edge connectivity K edge connected and edge connectivity K do not mean the same thing. There is a very nuanced difference that we have to be careful about as we go through this. All right, so we have our example for edge connectivity and edge connected. So now I'm going to introduce this quick theorem. This is by Whitney from 1932. So you might be thinking, well, the graphs that we work with were pretty small, but what if I was working with a much larger graph? And are there any quick upper bounds that we could work with? So Whitney actually showed that if I have a simple graph G, then I have that kappa is less than or equal than kappa prime, which is less than or equal than the minimum degree. So we have this here. So if I know the minimum degree, I can very quickly find an upper bound for kappa and kappa prime. Now, it may not be the best upper bound, but an upper bound is an upper bound. It gives us somewhere to start off with. So if I look at that graph that we've been working with, G, let's look at the minimum degree of this graph. Let's see, the minimum degree of this graph. Degree here is 3, 2, 2, 3, 2. It looks like the minimum degree is 2. So, by Whitney's theorem, we have this inequality, which also tells me since delta of G is 2, then kappa and kappa prime are at most 2. In particular, whenever I have this upper bound of 2, it gives me something pretty nice because proving 2 connectedness is pretty nice. Now we just have to show that no matter what single vertex I delete, it does not increase the number of components. So I won't actually prove this. This is a little bit of a nice theorem. There are going to be several theorems by Whitney that we will be looking at through this chapter. This is just one of them. Besides that, this is all for 4.1.